A Poisson process is a stochastic process that calculates the number of a certain kind, event or occurrence that occur at points in time. So for examples, number of emergency phone calls, number of births in a hospital, or number of website hits for a given period of time. A Poisson process has to satisfy three conditions. The number of occurrences in non-overlapping intervals is independent. Besides that, the probability of two or more events occurring in a sufficiently short time period is close to zero. That is, events occur singly and not in clusters. Lastly, the events occur at a uniform or homogeneous rate lambda. Lambda represents the average rate of occurrence or intensity of the events per unit of time. Then, lambda t, which is mu, is the average number of occurrences in t units of time. The probability mass function, f of k, is e negative lambda t times lambda t to the power of k over k factorial. If x is a random variable with Poisson distribution, then the mean or expectation of x is lambda t. For Poisson distribution, variance of x is the same as the expectation of x, which is lambda t. The PGF or probability generating function of a Poisson distribution is e to the lambda t times s minus 1. Note that we can use the Poisson distribution with mu equals to np as a close approximation to the binomial distribution when m is large and probability p is small. Let's look at an example to demonstrate this. Assuming that all days of the year are equally likely for a birthday and that birthdays are independent, we can use the binomial distribution with n equals to 200 and probability p equals to 1 over 365. Let x be the number of people born on December 31. Calculate the probability of 2 people born on December 31 using both binomial and Poisson distributions. Using the binomial distribution, f of 2 equals to 200, choose 2 times 1 over 365 to the power of 2 times 1 minus 1 over 365 to the power of 198, which gives 0.086767. Using the Poisson distribution, f of 2 equals to 200 over 365 to the power of 2 times e negative 200 over 365 over 2 factorial, which gives 0.086791. Note that the answer using Poisson distribution is very close to the answer using binomial distribution. Hence, it is a very good approximation when m is large and p is small. Now, let's look at a real-life example in an insurance company.
What is it, Ben?
It's New Year Eve now, but it's driving me crazy. Road accidents occur so frequently recently.
It happens every year.
It is bad. I've received several amount of insurance claims. On average, I have been receiving 3 clients' calls to claim insurance per hour. I wonder what is the probability that I won't be receiving any calls in the next 2 hours.
Well, that is easy to calculate. Since the number of calls follows a Poisson distribution with an average of 3 calls per hour, the probability you won't be receiving calls in the next 2 hours is exponential negative 6 times 6 to the power of 0 over 0 factorial, which is 0.00248.
What's the probability that I will be having 6 calls in the next 2 hours?
That will be exponential negative 6 times 6 to the power of 6 over 6 factorial, which is 0.16 or 16%.